to the afternoon session. So we agreed with Jakob that during the talk, the speaker will repeat the question, so we don't have to run with the microphone. During the Q&A, we'll give you the microphone in case you want to do a speech or something. Okay, so but keep it short in any case. So our first speaker in the afternoon is Marc Vinyals. He's going to tell us about the theoretical limits of one UIP learning.
Yeah, thanks, Albert. So yeah, I'll be talking not only about that, but in general, so connections between proof complexity and such solvers. So what can proof complexity tell about such solvers? So let's start with something we all know, the DPLL algorithm. This simple backtracking algorithm where we start guessing an assignment of variables. We branch if at some point we reach some conflict, that means a clause that is not that is falsified by our assignment, then we backtrack. And if we find that at some point some value should be forced, because one clause is unit and we need to set that value to propagate, then we unit propagate and we cut some part of the search tree. So that's DPLL. And if since it's a backtracking algorithm, we can think of its search tree, right, which is just all the branches variables would go through. And yeah, this is the search tree that would correspond to this formula. So we would start maybe by branching on X, then on Y. Then when we get Z, we would have a conflict, we would backtrack and keep exploring all the branches. And because this formula is unsatisfiable, we'll eventually explore all the possible search tree and find out that no, there's no solution here. Now, very useful tool to analyze DPLL is proof complexity, so the resolution proof system. Resolution is just saying that we can take two clauses, any two clauses from our original formula, and if they have a variable with different signs, we can resolve them together. And now if we look at the search tree, we reverse the arrows, so from upside down to bottom up, suddenly we have a resolution proof. So that makes us happy because now if we have lower bounds for resolution, we get DPLL lower bounds. Or in other words, if we know that the formula can be solved efficiently with DPLL, then that's because a short resolution proof exists. That's DPLL. Then let's move forward in time and talk about CDCL, which is, as you all know, this version of DPLL where we can be a bit smarter with our conflicts, and instead of just backtrack, we can go and learn some clause from our conflict, and hopefully we learn something that will be usable in the future. So if we look at this formula and this search tree, when we move down here to querying Z, and we were trying to figure out, oh, is it possible to assign Z to some value? We would go here, see, no, that's not possible here, that's not possible either. So that tells us that it's not a good idea to set both X to 0 and Y to 0 because we'll reach a conflict. But, well, the conflict, it's between these two clauses, and there's no X variable here. So this tells us that the conflict is not because of X. X has nothing to do about that. So we can learn something smarter than it's not a good idea to set X and Y to 0. We can learn it's a bad idea to set Y to 0. So we can go and record that and say, yeah, Y must be set to 1. And then when we backtrack, eventually set X to 1, and we try to figure out what the right value of Y should be, then it will we already know that it's supposed to be 1. So we'll cut half of the, or not part of the search tree, and our computation will be faster. So now, because we are remembering clauses, we're learning clauses, our state before was just the partial assignment. Now we have both a partial assignment and some learned clauses. And then there's a detail that will be useful in the future, that now it might be useful to forget part of the state. So that's something that doesn't make much sense with DPLL. But with CDCL, maybe sometimes we'll want to forget what our partial assignment was, and that's what we call a restart. Or we might want to forget some of the clauses that we learned, and that's what I'll call forget. Good. Then can we analyze CDCL the same way that we did with DPLL with resolution? Yes, we can still do that. And the technique is exactly the same. We just take this search tree, flip the arrows upside down. And now, because we are using learn clauses, so this is part of the search tree that we cut off. So now this is not going to come from one of our original clauses. Instead, it's going to come from one of the clauses that we learned before. But it's still resolution, not much changes here. Well, actually, something does change, which is that before we had a proof that looked like a tree, and now we have these clauses that are being reused. So we're going to some other more general form of resolution. So let's summarize what I said just now. So we have that CDCL produces proofs that are in resolution form, and we can use that to prove lower bounds on the runtime of CDCL. I also mentioned that proofs in DPLL are not general resolution. These are proofs that look like a tree. And in fact, we know from the proof complexity literature that tree-like and general resolution proofs can be very different. So tree-like proofs can be exponentially larger than general resolution proofs. So then that gives us one reason for why CDCL is better than DPLL, which is that it produces dog-like proofs instead of just tree-like proofs. But of course, well, DPLL was limited. Maybe CDCL is also limited by some other restriction, right? Could be that it's more general than DPLL, but it's still restricted to some other proof system. And this is a question that was investigated soon after CDCL was proposed. And a fairly good answer came in the late 2000s, showing that under a fairly natural model of CDCL, we can show that CDCL can do everything that resolution can. So let's be a bit more precise about that. Actually, there's a couple of theorems saying this, that CDCL can simulate resolution. So one is with non-deterministic variable decisions. That means that we're now taking our CDCL solver and we are in a sense cheating in that we have an oracle that every time that CDCL should branch on a variable, it's going to tell, yeah, that's a good variable to branch on. So please do that. So instead of saying that CDCL can find resolution proofs, I'll say can reproduce resolution proofs, because we have to tell the solver what the proof is before it can find it. Yeah, what the result says then is that if you have these optimal variable decisions, then if you have a resolution proof of some length L, then CDCL will be able to reproduce that proof with a small overhead, and we'll talk more about that later.
Mark,
yeah,
shouldn't there be restarts as well in this theorem?
There's going to be restarts. I'll mention that. And then there's another version of the result, which is, well, instead of having non-determinism, having an oracle, let's try having a solver that just throws random coins whenever it has to branch. And then what happens is that we can still simulate resolution, but now it's a special kind of resolution called bounded width resolution, meaning that the longest clause in your proof should be small. So if the longest proof in your clause has at most 10 literals, then CDCL will do that with time n to the 10 plus, I mean, a bit more than n to the 10, but something like that. Right. And let's then see how does one prove these results. I won't go into details, but just an idea.
The first result, why is it not already solved? Why is it partial? It seems to be completely solved.
Right. It's completely solved as long as you assume that this is the right model of CDCL. But you could think, well, in practice, of course, CDCL is not going to make this, it's not going to have an oracle to give it what variables to branch on.
But it's not deterministic, it's going to branch on all of them.
True. Yeah, so if we assume this, then there's not anything else to say. But if we want a model that captures reality, then we want to work with a more fine model.
I don't understand the model, how it can be different. Resolution is not deterministic. CDCL is an algorithm. Of course, it cannot precisely produce.
Of course, otherwise we would be automating
Yes,
resolution, and that's impossible. Right? So I completely agree with that.
So how can you improve this?
You can improve it by not that you can improve on this statement, but things that you could improve, for instance, are the overhead, or you could try to find out which assumptions are really necessary. So, but yeah, I'll talk more about that. So let's continue. Go ahead, Jaro.
Well, I mean, this is like, no, you could improve on this in different ways. This is like very much stronger than, this is an extremely strong complement to non-automatability, right? On the other hand, you know, on the one hand, you know you can't automate, but this says you can almost automate. You can take this extremely super concrete coded up algorithm, and you only remove the variable decisions. You leave like everything else as is, and now you're actually automating. And now you can ask this for, like, you know, maybe I could plug in a variable state independent sum decay decision scheme, but something, I don't know, do something to the variable deletion, the clause deletion or something, and maybe I'm again automating. So you can play this game with different heuristics components in your CDCL solver and try to pin down, like, where is the entry hardness.
So on that as well. So what is the difficulty of actually pinning down a decision heuristic and getting a tighter proof on that, a tighter result? What's the difficulty?
So what's the question? What happens when we fix a decision?
If you say instead of this non-deterministic, you orthogonalize branching, right? And you say, okay, any branching, but if you just say I have this fantastic branching heuristic, right? Mm-hmm. And include that in your analysis. Why is that difficult?
I'll answer this in 3 slides.
Okay.
But but turns out then you cannot automate.
Okay.
Good. So let's then see quickly how do we do this. So the idea is that we have a resolution proof. We would like to simulate that with CDCL. So the most natural thing that you would do is try to learn every clause in the proof. That makes a lot of sense. So how would you do this with the CDCL algorithm? You would try to falsify a clause, the clause that you want to learn. Hopefully you'll get a conflict and learn that clause. So if that happens, great. And well, while this is a great idea, it doesn't work, but still it can be patched because we don't really need to learn every clause. Everything that we need to do is to fool the solver to think that it has learned that clause. So if every time that the solver would make a propagation because of this learn clause, it still happens because of some other clauses. And every time that there's a conflict, it still happens, then the solver won't notice whether it has learned that clause or not. So, okay, fair enough. Then we can use that idea, which is really the key behind those 2 results. And instead of learning clauses, we just act as if we had learned them. And then we have simulation of resolution by CDCL. Right. Now, well, we were talking about the model. Which assumptions do we need to make for this algorithm to work? Well, they are the following. So first, we need to assume that the solver is making optimal choices. Because every time that we have to branch, what we do is pick one of the literals from the clause we want to learn and set it to false. So here, we really need to know what the proof is, which proof are we trying to reproduce, and we need to make these choices. Then another assumption is that we're not throwing any clauses away. And another one is that we are restarting fairly frequently. Actually, here I'm cheating a bit because I'm restarting immediately after learning, but it's not too important. And we're also assuming that we do some standard learning so that when you learn a clause, that's a clause that's related to your conflict. If you learn a clause that has nothing to do with your conflict, then that's not really CDCL. Yeah, then let me answer your question, Karim. What happens when we fixed, so instead of having these optimal variable choices, we fix branching? So the first thing to observe is that we really need optimal variable choices, because otherwise we would be contradicting some result in theory, saying that if some algorithm, some deterministic algorithm could simulate resolution, so find short resolution proofs, then P would be equal to NP. And that's something that Albert and Moritz proved a few years back. So we really think that we need that assumption. But well, maybe we can still try to play with specific decision heuristics, see what happens then. Yeah, and then there are some results in this direction. For instance, if you have a static order, so you have a variable order that doesn't change at any point during solving, then there are some formulas where that does exponentially worse than resolution. So the formulas that have short proofs, but cannot be done with a static order. Or if you choose visits or anything that's conflict-driven branching, then there's also going to be some formulas where they have short resolution proofs, but because of this branching heuristic, the solver will run in exponential time. Now, one drawback about this is that the formulas are fairly contrived. It's not something you'll see in practice. But you could still try to design a heuristic that will not be affected by that and see what happens in practice. And turns out that there are some instances where some modifications of visits can work better. And you have to ask Vijay if you want to know more about that. Good. So that was branching. Now, I also mentioned that this simulation is an efficient simulation in the sense that if you have a proof of length L in resolution, you'll get a CDCL proof in about n to the 4th times L steps, so polynomial. Can be improved to cubic. And now that's something that I'm happy with. It's a polynomial, I'm happy. But if you're building a solver that runs in linear time, then you are not happy. That's too much. So can we improve this simulation overhead, or maybe it's really needed? We need some overhead. And here again, it turns out that there is some overhead that's needed when you use CDCL. So now let's think of a model of CDCL where really it can do anything that you want. So do you want optimal variable choices? You've got them. Do you want to restart whenever you want? Sure. So just give all the tools that the solver might have. It's of course going to be able to polynomially simulate resolution, because it's so the best separation that we could hope for is a polynomial. But still, there are some formulas that have linear proofs in resolution, yet require quadratic proofs in CDCL. Right. So how would one go and prove that? Well, the basic idea is that the kind of clauses that CDCL learns have some syntactical restrictions. So we can build a proof system that incorporates those restrictions and then prove a separation between these restricted versions of resolution and normal resolution. So again, to give a flavor of how that can be done, when CDCL learns a clause that's conflict analysis, it will start with the conflict clause, and then it will take a reason clause and resolve them. Then it will take another reason clause, resolve them, and so on. So learning a clause will look like this input resolution sequence of derivations until we reach some clause that can be learned and reused later.
All the literals in it? Or was it just a number of steps?
The question was, does the length of the proof include all the literals or just number of steps? This is length, so only number of steps. So the total size could be larger. The proof that CDCL produces will look like this sequence of derivations. Then there will be some lemma that we can remember and maybe use in the future. But so far, there's no restriction. So a normal resolution proof can also look like that. Just you can have trees that have just height 1, and then this will be exactly the same as resolution. So what makes a difference is to say, let's impose some conditions on what these learned clauses, these lemmas can be. One very natural restriction would be to say that everything that I learn must be one empowering. So that's the converse of observed, meaning that if a solver learns a clause, then it does so because it enables the solver to do more unit propagations in the future. Otherwise, it's a redundant clause. There's no need to learn it. That's very natural, but it's also a very annoying proof system to work with. So instead of that, there's a similar restriction that we can do, and it's to ask all lemmas to be merges. So a merge is a resolution step where we have two clauses sharing literal in addition to a variable with opposite signs. And then this literal will get merged when they are getting resolved. So that's what happens. And turns out that merges and one empowering clauses are fairly related. So it's not, it really makes sense to ask for this. If you work with a learning scheme like first UIP, then you get exactly this restriction. And by doing some modifications, you can actually also capture other learning schemes, but I won't go into details.
How are you going to get the empty clause?
Are you going to get the empty clause? Well, so the very last sequence does not have this restriction. So just to summarize what I said, we can have this proof system. Let's call it merge resolution because it builds on some proof system from the 60s. Where we ask learned clauses to be merges, and that's what we do then. So we can show that the kind of proofs that CDCL produces will always be in this form, and we can show that there's a separation between normal resolution and merge resolution. Well, that was the result. So now, where do we go from here? Just staying on this topic of overhead. Right? We explained one linear factor in the overhead, but the overhead was cubic. So what about the other n squared factor? Can we explain that? Can we remove it? What can we do there? And if I take a proof in this restricted merge resolution proof system and give it to a CDCL solver, will it do better than if it only had the resolution proof system? I don't know. And maybe similar to what happened with branching, where we expose limitations and then you could design branching scheme that avoids those problems. Is there a way to do learning that avoids this kind of problems? And then staying still with the CDCL versus resolution topic, I mentioned a few assumptions and quickly discussed branching, but there were a few more assumptions that we had to make. For instance, that no clauses are ever being deleted and the solver restarts frequently. There has been work in both these questions, but I'd say that there's much more we would like to know. And then, well, let's leave resolution behind and think longer term. Resolution is great for capturing CDCL, but solvers nowadays do more things than CDCL. They do pre-processing, they reason with parity and pseudo-Boolean constraints, they do symmetry breaking. So what can proof complexity say about all these things? Unfortunately, it can say things about parity and pseudo-Boolean constraints. There are proof systems that can deal with this kind of constraints. but preprocessing, symmetry breaking, they're just too strong. So the proof systems that we have that can capture these techniques, we cannot say anything meaningful about them. So that's very annoying, and it's not clear if we can do anything. So can we define proof systems that are more tailored to what solvers are doing in practice and then say things about them? That would be great.
Can you repeat this question?
Yeah, so the question is, we can model things that solvers do, like preprocessing and symmetry breaking, using very strong proof systems, such as extended Frege. But we cannot say anything meaningful about the extended Frege. So could we define then a subsystem of extended Frege that can still capture maybe not all, but some of these techniques, and where we can prove lower bounds? It's something like this has been done by Sam and Neil, for instance. So there is work in this direction. Things are happening. And then maybe there are some questions where maybe proof complexity will not be the right tool. So what can we say about satisfiable formulas? Can proof complexity say something about them? Maybe, maybe not. Fairly agnostic about this. Or the question, when is CDCL efficient? Proof complexity will be able to answer or tell you some reasons for when CDCL is efficient. If there's a short proof, then maybe it can be found. But the fact that there exists a proof, we've seen that doesn't mean that CDCL can find it. So then what are the properties of formulas for which CDCL can run efficiently on them? This is a very, very hard question. We don't expect to find a close answer to this, but is there anything we can say? I mean, again, there's measures like true width that can answer this question in practice, in theory, sorry, but not so much in practice. There's measures from the practice side that can show correlations, but don't mean much in theory. So what can we say over there? And that's it for me. Thank you.
Any questions for Marc?
Hi. So about your last previous slide, so satisfiable formulas, for instance, there are these results about Novich and all.
Yes,
Is
this
this
is
related?
drunk.
Yeah.
Yeah.
So yeah, another thing is pre-processing and symmetry breaking. I mean, there are these parity and pseudo Boolean constraints. There's a lot of supposedly weak proof systems that model these in some sense, no? Pre-processing is basically effective simulation and maybe resolution. Parity and constraint is just Reslin or something like that.
So things like parity and pseudo Boolean we can handle, but it's more of the pre-processing and symmetry breaking that we are more lost with.
Okay.
Okay, so these are open problems. What about when a CDCL is not efficient? I mean, is there something beyond CDCL that we got stuck, for the past, 2.5 decades, kind of just doing this? Is there something else that we can look at?
Yeah, I mean, there
beyond,
are these
local search. But you see what I'm saying? I mean, I'm just curious as to why are we in this and why does this work? And is there no way to answer that question?
No, it's a great question. And there are some things like pseudo-Boolean solvers. There's SDCL.
Yeah. So you need to go to other kind of, and that goes to my point in the morning, which is if we're solving a real problem, right, which is coming from somebody's head, maybe a CNF encoding for it may not be the right way to kind of reason about it. And we need to go to these other things that describe it more naturally.
I think you're right.
Like polynomials?
Well, SMT solvers do that all the time.
Sure.
Basis.
Yeah. I'm not saying anything weird. I'm just saying, you know, we focus on difficult problems in CNF when in fact, you know, let's move on.
You mentioned that
I'm sorry.
if you have VSIDs, it was exponentially worse than resolution. I'm just wondering if you have any lower bounds. If you don't have anything, you don't even have VSIDs, would it be doubly exponential? It might not make sense, but I mean, to me, the activity scores keeps you focusing on part of the problem instead of trying to solve 100 problems at once. And so I was just wondering if there's any lower bounds on what's VSIDs done.
I would think that even worst case, if you're doing DPLL, you wouldn't do worse than exponential. But yeah, you shouldn't do worse than exponential. Yes.
So these results that you mentioned are about worst case complexity, right? There exists a formula for which there's a linear resolution, but so do we know anything about average case?
The challenge, if I may add there, how do you define average?
Yeah, I know, but what I'm
Yeah.
saying is looking at the worst case, of course, has its benefits, but it also completely, you know, turns a blind eye towards maybe what's happening in practice.
Yeah, no, Vijay's point is that I don't know a good way to define average case. If we think of average case, that would be random formulas. Those are hard, period. So that's not very interesting. If we would like to say industrial instances, great, but we don't know how to define them. So it's more of a definition problem, I think.
Okay, let's thank Marc again.